Hello everyone, in this lecture I'd like to set out the details of block internals of a simple blockchain implementation mainly based on the Bitcoin protocol. We will also touch on the mining basics of the same distributed network of nodes that transfer value in complete decentralized fashion. This lecture is not going to cover all the working principles of crypto networks or cryptocurrencies in particular, such as authentication, authenticity, security aspects of the blockchains, the convergence of blocks or the consensus. So I'll refer you to the appropriate references listed at the end of the presentation. Alright, so let's start by looking at the data from its size perspective. We can classify it, the data in terms of size, as shown in this slide. It can either be comparatively small, the size, or it can be greater than a threshold. Okay, for example, it's 2 gigabytes. If we classify it as large size data or we classify it small size data, we can think of the small size data as transaction data or metadata or short text messages that may bear, valuable information. On the other hand, large size data includes bulk data or raw or compressed multimedia data. These two blocks can be related to each other. For instance, a distributed file system can have metadata that manages the user data, and both can be distributed over the network nodes. Blockchain stores small size data in a chain of what's called blocks. For the rest of our discussions, we'll be focusing mostly on Bitcoin protocol, while as of today there are other implementations of blockchain for different applications. Okay, so blocks can store only limited amount of information. Okay, so every block in the Bitcoin network has the exact same structure as the table shown in the slide, and each newly created block is chained to the last added block of the blockchain and stores its digital fingerprint. So there are, as you can see, 5 different fields in a block. The first field is called magic number, which is 4 bytes, and it's an identifier for the blockchain network. It's a fixed value, actually, a constant value. It indicates the start of the block, and the data comes from the production network. Block size, which is also 4 bytes, indicates how large the block is. Initially, the block size was fixed to 1 megabyte. It's quite a traditional choice. The core development team, who can change the protocol rules and etc., can increase it to 2 megabytes. So the maximum capacity is 2 gigabytes. So the scalability factor is taken care of by small size data. Block header contains is the next field. It contains 6 sections or 6 subfields, which we'll cover later, and it takes up 80 bytes of space. Transaction counter gives us the number of transactions contained in the block, and we essentially store digital signatures of transactions in transaction list section, which is the last subfield. The amount of transactions that can be stored in the block is limited by the block size, which might be typically 1 megabyte. Okay, so let us look into the details of the block header. There are 6 different subfields. Version number tells us the version of the protocol, and it's mentioned in this field for everyone in the network. It is updated when the software update happens. The header also includes previous block's hash number. This data field is actually what makes it a chain-like structure. It is typically updated when a new block comes in, and transactions are stored in the blocks as a binary hash tree, also known as a Merkle tree. The tree has a root, and it's the hash of all transactions contained in the block. So we will talk about it later. The time field stands for the current timestamp, which is expressed in Linux time format, and it's updated almost every 5 seconds. The time is represented by 4 bytes, and we will see an example of it later. The next field, subfield, is the bits field. Bits field is used to adjust the difficulty and nonce. And this nonce is a 32-bit counter, which is incremented every time a hash is tried by the miner. We will talk about these 2 fields in detail when we discuss technical details on mining. Okay, so if you are to draw an illustration of how a block structure looks like, this might be it. Here how it looks in 8-byte column structure called the block structure. The number of transactions is assumed to be even, and a multiple of 8 bytes are used to fill the structure to result in a rectangle shape as shown in this slide. Block header includes version number, the previous block hash, a Merkle root, a timestamp, and difficult to target, and nonce, which make up 80 bytes of information, as you can observe from this picture. Okay, so next we look at the Merkle root. How is it calculated? Okay, so Merkle tree is a nice way of storing short-sized data, such as transactions. So the data itself is not stored in the tree, but the hash values themselves. The root of the tree is the topmost node, and hence this tree is represented upside down as shown. The bottommost nodes are called the leaf nodes. Each node is simply a cryptographic hash of a transaction. The leaves of the tree are the hash transactions, for example, A, B, C, and D. Then we move up in the tree, we concatenate the hash values of children nodes and hash the concatenated values to generate a combined hash. Finally, the root node combines the hashes of all transactions to create a merged hash. For example, in Bitcoin protocol, hashing is defined to be a double, SHA-256 algorithm, which ascertains proved security against, for example, collusion attacks. But that's a detail. Merkle tree makes it extremely easy to check whether a transaction is included in the block. You could have, for example, used different types of, hashing algorithms, but you have to make sure that, you have enough security in your system. Alright, so let's also talk about a special transaction, which is called CoinBase transaction, and is a special type of first transactions in all the blocks and is the source of new coins. In other words, that the generation of fresh coins are due to this transaction. This transaction, the miner can assign himself inside that transaction, can assign himself so many bitcoins defined by global rules and changes based on the cryptocurrency used. The leftmost transactions of the Merkle tree is where the Coinbase transaction is hashed to. So this transaction also has a field called extra nonce, and in which, for instance, nonce can be stored. For instance, Bitcoin protocol does this actually. So since the counter parameter is small, like 32-bit counter, it can be reached easily. As the difficulty increases, you try and try and try, and in each try you increment that number. So every time you reach to the maximum number that can be stored by nonce, it wraps. So every time it wraps, extra nonce parameters is incremented. So this would lead to the change of Coinbase, and hence the Merkle root, actually Merkle tree root, making the the miner's job a lot harder job to do. Okay, so let's also specify some of the more information about Merkle trees. As can be seen, Merkle tree allows very easy and efficient verification of the contents of large data structures. That's the first thing to know. Secondly, we note that the number of transactions do not change the total effort. If you have one transactions in the previous 4-leaf Merkle tree example, we copy these transactions 4 times. You can copy transactions to make it 4 and then hash it. So the average amount of effort to generate the tree will still almost be the same. And final observation is that if a small change happens in one of the transactions, or if we add other transactions as a leaf node, we have to redo all the computation for Merkle tree root calculation. In fact, it's not hard to see that the number of hash recomputations is a log n, where n is the number of leaves. Okay, so let us also discuss the difficulty, how it is managed by blockchain network. So let's start with the bits field, which is hexadecimal target in expressed in compressed form, which takes up 4 bytes. Original target is 256 bits or 64 bytes long, and this can be calculated from the compressed form using a predetermined mathematical relationship or equation. And this is actually shown in this slide. For instance, suppose bits field is 0404CB, which is a signed number. Then the 256-bit target is as given. So it's a kind of one-to-one map here. So let's define highest possible target to be difficulty 1 target. And we note that traditionally it represents a hash value with 32-bit long, actually 32-bit leading 0 bits, and the rest is all 1. So therefore the difficulty is calculated as difficulty 1 target divided by current target. So in our example, we can calculate the difficulty to be 16,300. Okay, so here's another example. There might be some implementation specific details such as hashes, ordered in terms of internal byte order, and the rest of the values in the block might be ordered based on little endianness, for instance. On the other hand, transactions in the block might be ordered, and that may also change the Merkle tree rules. Ordering might be based on the timestamp. In other words, how old the block is and the value of transactions. In other words, for example, aggregate input and output values so that you can basically order these, and that's going to change the entire spectrum of the transactions, and due to the hashing, Merkle root will also change. So after learning about the details of blocks, so let's look at the bigger picture of mining in a blockchain and consider how these fields interact with each other as the network evolves and puts more and more blocks into the chain. So we have a copy of the whole blockchain in our local. We create a new block, or we receive a block from the network, and our job is to mine this. By mining, the mining operation, that is actually handled by a client software that we download and execute. So the mining is not about earning currency in such networks, but it's the maintainer of the network and allows the chain to grow, bigger. Otherwise, the value transfer would be impossible. So we begin with hash calculation of the block, and we compare this number to a target value determined by the network, and we know where the target is located. So if it is less than the target, then we increment nonce and try again until we succeed. Or network informs that some other miner already found the answer to the question, in which case we verified it and acknowledge. If none of these happen, we succeed and broadcast our solution until we get confirmation. In that case, we add the block to blockchain, and in turn we receive some credit for that. Usually it's coins in cryptocurrency world, and this is also called incentive. At the background, nodes in the network, since they have the chain, copy, they see if 2016 block since last adjustment arrives. In that case, the target value is readjusted, and this is done to make sure that on average it takes around 10 minutes to solve the hash problem mentioned here. Alright, so with this short presentation, we focused on the internal details of the blocks and the blockchain network. There might be many variations to its implementations as the range of applications emerges vastly in the last couple of years. So it looks like it's quite likely to see different block structures addressing different requirements of various applications and their associated implementations. Thank you for your attention.